Stars, full of hydrogen and helium powered by nuclear fusion. These are seen from billions of light years away. But do they last forever? Do they have a start, an end? They, like us, are born, they live, and later they die. A star's life first starts out in what we call a nebula. A nebula is basically a big cloud that's in space, which is made mostly of hydrogen with some helium and dust particles. So what starts the star inside the nebula, a bunch of gravitational instability occurs, which pulls in a whole bunch of mass from the nebula. So the more mass there is in this gravitational pull, the more gravity there is. So once this gravitational pull starts, it forms what we call a protostar. And over time, temperatures increase to about 15 million degrees Celsius. And it starts what we call nuclear fusion. Just as a side note, nuclear fusion is a form of energy where hydrogen molecules are joined together to form helium molecules. This only happens at really high temperatures. Once nuclear fusion starts, the protostar becomes a star, and it reaches a stage known as the main sequence stage. Sometimes the protostar doesn't reach high enough temperatures to become an official star, so instead of a star, it becomes a brown dwarf. The main sequence stage lasts for a long time, depending upon the mass of the star. If the star has 5 times the mass of our sun, then it may only last for 10 million years. If the star has about the same mass as our sun, then it may last for 10 billion years. If a star has less mass than our sun, then its main sequence stage may last to up to 200 billion years. The reason why stars with less mass last longer is because they have less area and less atoms to maintain. Once a star nears the end of its main sequence stage, it really depends upon how much mass it has. Once a star that has less mass than our sun runs out of hydrogen to fuse into helium in the nuclear fusion process, once it runs out of hydrogen, then the main sequence stage for that star is over. Once it's nearing the end of nuclear fusion, this small star expands and becomes a red giant in order to get more hydrogen. Slowly, over time, the outer layers of the red giant star will just drift off into space and will create a planetary nebula around the star. Slowly that dissipates, leaving the core of the star. The core tries to achieve nuclear fusion, but it can't. So, it becomes what we call a white dwarf. A white dwarf is still very hot and very bright from leftover energy that it had in the star, but it doesn't create any energy. Over time, that energy is drained away, and it dies. It becomes what we call a black dwarf, which gives off no light and no heat. This same process happens to medium-massed stars like our sun, except for one thing. The medium-sized stars, when they're done burning up hydrogen into helium, they start burning helium into carbon. They can do this because they have higher temperatures. This is still nuclear fusion. Once they run out of helium, though, then they expand and do the same stuff as smaller mass stars. But with stars that are at least 5 times the amount of mass as our sun, now that's a different story. Once they're done burning hydrogen into helium, they start burning helium into carbon. But once they run out of helium, they start burning carbon into neon, sodium, magnesium, sulfur, and silicon. After they're done with the carbon, they use the other elements and they fuse them into calcium, nickel, copper, and other elements, mainly iron. When copper starts being fused, the star expands into what we call a red supergiant, and this is huge. While the elements are being fused into iron, then nuclear fusion stops. The star just can't take it anymore, and the whole core collapses. During the collapsion of the core, protons and electrons are being smashed together to form neutrons. Also during the collapsion, the core releases tons of gravitational potential energy, which causes the whole thing to explode in what we call a supernova. A supernova can be as bright as a whole galaxy of stars put together. After the explosion of the supernova, all that's left is just a core full of neutrons, and the neutrons in the core keeps the star from collapsing again. Now this is called a neutron star. A neutron star is about 20 kilometers in diameter and is about 1.4 times the amount of mass as our sun. That's really dense. A neutron star, like a black dwarf, is the end and the death of a star. But there's another type of star that has even more mass than the one that forms a neutron star. This type of star still forms a red supergiant and still explodes in a supernova, but it doesn't form a neutron star. After the supernova explodes, it forms a black hole. After the supernova explodes, instead of forming a neutron star, the whole thing just collapses on itself and gets into a really small amount of volume, but has tons of mass and density. The black hole begins to pull in many things around it. In fact, there's a line around the black hole, an imaginary line called the event horizon, that if anything passes it, including light, if anything crosses that line, it gets pulled in, no matter what. When I say everything, I mean everything, including all the electromagnetic radiation, any type of super fast rocket, or light. Everything gets pulled in. Since light cannot escape, we can't see black holes. Therefore, these pictures of black holes are pretty much artists' ideas of what a black hole looks like. Black holes are very mysterious at the moment because we just don't know a whole lot about them. So there you have it. Starting in a nebula and ending in a black hole, a black dwarf, a brown dwarf, or a neutron star. That is the life of a star.